last video, we tried to define the linearity conditions of equations, but we hadn't actually formally defined what equations were. So let's do that now. And after that, we will move on to equations or functions or expressions that contain more than one variable. So equations are expressions equal to constant. In our context in linear algebra for this course, we're specifying that an equation is of the form an expression is equal to a constant. So let me give you an example so it becomes easier. So ax squared plus bx equal to minus c is an equation. So you might immediately ask me, what if I wrote ax squared plus bx plus c equal to 0, which is normally the way you would write that quadratic equation. That is not the way we would like to write it for our purposes in this course. If you ask me, is the other one not an equation? Sure, it's an equation, but not for us in this context. Another equation that you might come across is y equal to mx plus c. That is an equation to a line, but we will write it as minus mx plus y equal to c. So in general, an expression equal to constant is an equation, but you know that a function is basically a named expression. It's an expression with a label. So a function equal to constant also is an equation. Now, when I ask you if an equation is linear or not, the only thing you can do is to look at the expression in the left-hand side and see if that is linear after having collected all the constants to the right-hand side. Now, collecting the constant to the right-hand side, I'm going to put a condition here saying that you can use only addition and division, or they occur in subtraction and multiplication, to move the constants to the right-hand side and the variables to the left-hand side. So those are the only things you can do. In particular, you cannot take square roots or cube roots or exponentiation or inverse functions or anything. This is the only thing you can do. That's for this course, the way I'm running it. So if you ask me in general, is it wrong to take the square root on both sides, etc.? Yeah, it depends on your context. It's not for this context in this course. This is why I said this is the course that will take you to some kind of mathematical maturity. All these things, like I said, are just tools in your toolbox that you can use to solve problems that you encounter. And the best way of using it for this course is by saying that constants have to be on the right-hand side, expressions on variables will have to be on the left-hand side, etc. But you might find it completely fine and even advantageous to use something differently later in life, but go ahead, do it. Don't say that prof said, oh, equations are expression equal to constant, so this is not an equation, so I cannot do anything here. No, that's not what I'm saying. Right, moving on. The real thing to understand here is the fact that the equal sign that appears in an equation, this equal sign, is a bit different from the equal sign that appears in the definition of a function, this equal sign. In this case, when you say fx equal to an expression, you're just assigning a label to that expression, calling it f in one single variable. That is like an assignment. It's like an assignment in a programming language. In some languages, they have a different symbol like that for assignment. But when you say an expression equal to constant, this equal sign is a different kind of beast. This is actually a statement of truth. We are requiring the expression to be constant. In other words, if the expression is an expression in some variables, we are finding or we are looking for those values of those variables that will make this equation true. It's a statement of truth. So it's kind of like a logical assertion in a programming language or a conditional statement where you have equal. So the thing to understand that in mathematics, single equal is actually overloaded. So it's got multiple meanings depending on the context. So it's something to keep in mind. Now, linearity of an equation is basically just the linearity of the expression in expression equal to constant after having collected all the constants to the right-hand side and all the variables to the left-hand side. Look at the expression, and if that expression is linear by our definition or conditions that we specified, homogeneity and additivity, then that equation is linear. And if I give you an equation that says expression 1 equal to expression 2 and ask you if that is linear, first of all, you are free to complain. You can come and tell me this is not a well-posed equation, because equations are supposed to be expression equal to constant, then the second thing you can do is to basically do equation manipulations so that you get expression equal to constant, but using only additions and division, or subtractions and multiplications. And then you can check for the linearity of the expression to determine the linearity of the equation, of which the expression is the left-hand side. Now let's see what's wrong with our equation y equal to mx plus c. Why did I say that this was not linear? Why? Clearly, this is an equation to a line. Let's look at that. What I'm saying is that if I write an expression mx plus c and call it by a label f of x in one variable, then this expression is clearly not linear because f of 0 is not 0. Unless, of course, if c is equal to 0, then it's fine. If c is not equal to 0, then this is not linear. But we know that it's a line. So where are we messing up? Now the equation to a line is y equal to mx plus c. But this is not an equation in our well-formed linear algebra way. We have to rewrite it as minus mx plus y equal to c. Now if you look at the left-hand side, it's not an equation in one variable. It's got two variables. So it's got x and y. It's a function of two variables if you were to assign a label to it. And then since it's two variables, we don't quite know whether it's linear or not. We haven't specified the conditions of linearity for expressions in multiple variables. We did it only for one variable. So let's do it for two variables. So we will say that homogeneity is if you scale the inputs by a certain factor, s in this case, same factor, not different factors, the output should scale by the same factor. That is homogeneity. I'm specifying it now. Similarly, I'm going to say that additivity condition is satisfied if you split up one input in two parts and the other input in two parts also, and then the output splits up in such a way that it's the sum of the outputs for the first parts plus the sum of the outputs of the second parts. This is actually very difficult to say in language, in English. So let me just read this out to you slowly so that you can understand this. So f of x plus x prime and y plus y prime is equal to f of x and y, the first parts, plus f of x prime and y prime, the second parts. If that is true, then I'll say that the additivity condition is satisfied for two variables. So this is what I'm going to say about homogeneity and additivity, and I'm specifying those things for multiple variables. Now, after having said that, let's look for the linearity of this expression in two variables, or the function of two variables. If I scale both by s, originally my expression was minus mx plus y. Now I will use sx wherever I see x and sy wherever I see y. So f of sx and sy is minus m sx plus sy. S being a common factor, you can pull it out. Then that becomes the original value of that expression multiplied by s, the same factor. So homogeneity condition is satisfied, the extended homogeneity condition. Similarly, I can take x plus x1, y plus y1 and do a little bit of algebra there, and then you will see that additivity condition also is satisfied. So by my extended generalized definition of linearity, this function of two variables is actually linear. So as a function of two variables, this guy is indeed linear. But as a function of one variable, mx plus c is not linear. So there's no contradiction here. It's just the context. One is one variable, the other one is two variables. Now let's take one more step and make the statement that f of x equal to mx plus c is linear only if c is 0. That means the only linear expression in one variable is mx. So instead of m, let me call it a. So the only linear expression in one variable ax, and the only linear equation in one variable is ax, the expression on the left hand side equal to a constant. Let's call that b. The only linear equation in one variable is ax equal to b. I like this, and you will see why maybe in the next video, but this is something that you will remember for the rest of your life. So now that we've defined linearity for multiple variables, expressions in more than one variable, you will see that that kind of naturally leads to the notion of vectors and matrices, and that will be the next video.